a few years back. And I'm Rajesh Nair. I am from the Department of Physics at IIT Ropar in Punjab. So the picture you see here, few diamond samples in our lab, like few centimeter size diamond crystals. And if you shine these crystals with a 532 nanometer laser in the right picture, you can see a nice red glow. Basically, it's a fluorescence from these color centers or the nitrogen vacancy center in these diamonds. So I'm going to talk about the interesting aspects of these things and why we need to study these things, what are its uses, and why this so much craze about nitrogen vacancy centers for quantum technology, and what are the advantages and disadvantages. So before I jump into my talk, so we started our group at IIT Ropar in 2014. So we work in many aspects of light matter interactions. One of our prime research initially was on photonic crystals, which is a periodic structures at optical wavelength scales. We also did some research, or we're continuing on disordered photonic structures, not completely random, but there are some short range order within the systems. And we also working on metamaterials, low index and high index, or meta surfaces, which is also interesting system to manipulate light matter interactions. And of late, around 2017, we started, or we ventured into the diamond color centers, which was an exciting topics, and how we can integrate that to photonic structures, which I'm going to spend a lot of time today. And this is basically some images of NV centers spread on a glass substrates. And then very recently, we started also a new direction of research where in terms of quantum emitters in 2D materials, single and multi-layer 2D materials. And we are having very promising results, and probably we'll discuss that at some other point of time. Okay, so before you get into nitrogen vacancy centers, why we need this kind of system? In general, we call these a quantum emitters. It can be nitrogen vacancy center or other emitters, even quantum dots. So one of the primary things, though, there's so much interest that generated this thing because it can give single photon emissions, which is a workhorse for quantum technology applications. And some of the system can even have single photon emission at room temperature. And it has a long coherence time, and you can manipulate its spin states, and you can create superpositions. And we can also do a lot of sensing application using that. And it can be tunable to many other frequencies, and it can be integrated to photonic structures. See the picture you see here, there are some structure where there is a quantum emitter, which is a quantum dot in this case. There are some other structure, and there is a quantum emitter. We try to probe this. And there are nanowire kind of structures where some emitter is trapped, and some 2D material again trapped in some photonic structures. So in all these pictures, you see that these emitters are somehow trapped it in some photonic structures. And I'll tell you in this talk, I'll try to convince you that why we need to do that. Okay, and so there are many quantum emitters. The initial structures material was quantum dots. Then in the last few decades, the things more interest to diamonds or silicon carbide or the other type of systems, because they have very added advantage like room temperature operations, and one can manipulate its properties using light and microwave frequencies. So what is this specifically about color centers in diamonds? So it comes in different names. Sometimes people say defect centers, vacancy centers, color centers. And by color centers, because depending upon the type of vacancy you have a different colors in the diamond. For example, you have same diamond with a different vacancy centers or the different doping level, then you have a different colors. And this is shown as a system which can give single photon source at room temperatures. One can manipulate it using optical and microwave fields. And it's a very good material for quantum sensing applications. And even there are high resolution imaging like nano MRI and all people are trying to develop using the systems. So there are many defect centers in diamond or color centers in diamond. One can have a nitrogen or a chromium, silicon vacancies. And depending upon the vacancies, its optical properties is tunable. If you have a nitrogen vacancies, you have a property somewhere in the visible, centered around 660 nanometer. But if you go to silicon vacancies, then it will push towards near infrared vacancies. Near infrared wavelengths. Diamond is not the only material. There are many other wide bandgap material like the silicon carbide or zinc oxide or hexagonal boron nitrate. They're all been proposed as can host color centers which can give single photon sources. But again, the choice depends on its fabrication capabilities, tunability, and many other some aspects which I'll cover it today in the talk. So what is this color centers or a nitrogen vacancy in diamond means? Basically, if you take a diamond crystal where you have all our carbon atoms, and if you kick away two carbon atoms, and you have two vacancies, one is here, and another this vacancy is now replaced with the nitrogen atom. And this pair, which is a nitrogen, and close to that a carbon vacancy, this is called a nitrogen vacancy. And this vacancy is in the lattice points, whereas other vacancy like a silicon vacancy, it does not comes in the lattice point, but it is between the midway between the two lattice points. So you have a vacancy of carbon atom here, and there is a vacancy here, and the silicon atoms in the middle of that two vacant carbon atoms. So this is another kind of vacancy called silicon vacancies. And there are even more than 500 defect centers in diamonds, but few are explored. And if people are able to fabricate it, like a recent reports, there are tin vacancies and chromium vacancies and so on and so forth. And depending upon its vacancy, as I said, its emission properties will vary. For example, nitrogen vacancy have a centered around 660 nanometer, the red curve here. And if you have a silicon or nickel vacancies, the spectra is shifted to the long wavelength. So this is so we can have different vacancies to fabricate these samples and do a lot of interesting stuff with that. So it now becomes slightly more technical. So, so as I said in the last slide, so nitrogen vacancy is a pair. You have a vacancy of carbon atom, and close to that a nitrogen atom is placed, and this pair is called vacancy. And diamond is a wide bandgap material. It's around 6 electron volt. And because of this, the nitrogen vacancy or the defect state you create, you have energy levels within the band gap. And these energy levels are now, you have a triplet ground state and triplet excited states. And one can excite using a 532 laser. You can lift the population from the ground state towards the excited states. And on the this population can come back to ground state by two ways. Either you have a direct transition from top to bottom, or it can also take an intersystem crossing, slightly a long-term process. Okay, and these transitions can have two kind of nature. One we call is a zero phonon line. Basically, there's no phonon involved in these transitions, which comes at 637 nanometer. And there are transition between vibronic levels, and that will give you a huge phonon side band contributions. And these the ground state splitting between these two levels at zero magnetic field is 2.87 gigahertz. So one can apply microwave and manipulate the population between the states in the ground state of the nitrogen vacancy center. One can also apply a magnetic field, and you can split this degenerate level like a Siemens splitting. And these are the basis of the optically detecting magnetic resonance and magnetometry and magnetic image. So I'll be show you in the last part of my talk some of our recent result on applying microwave to a nitrogen vacancy center. And this nitrogen vacancy can be in two configurations. We call it a neutral vacancy, NV0, which has a 5 electron systems, and you can have a nitrogen NV minus, which is a 6 electron system. And accordingly, you have the spins are also different. So if you look in terms of more spectroscopic detail, you have a ground state electronic level, and you have an excited state electronic level. And these levels even have a vibronic levels. And you excite with the 532 nanometer, and you have a transition from the lowest in the excited state, which is a 0 here, and to the lowest in the ground state. There is no phonon number exchange happens here. So it's a pure electronic transitions, and what we call is a zero phonon line. And you can have a other transition between the vibronic levels. And so you have a huge contribution from the phonon side bands due to these vibronic transitions. So if you measure the PL spectra or an emission spectra of a nitrogen vacancy center, you plot intensity as a function of wavelength, you get a very, very broad spectra. And this small kink you see here, which is at 637 nanometer, which is this direct transition, which is a zero phonon line, the pure electronic transition, which is actually very, very weak. I have to even put an arrow to show you. But you can see that the spectra is dominated by huge phonon contributions from this lattice. And that is one of the biggest challenge in using NV sender in many applications. And here we define a parameter we call a debye wall factor, which basically tell you how much is the emission, which is channeled to zero phonon line over the total emissions. And this percentage of emission which get into the zero phonon line is 2 to 3% at room temperature. And even if you cool down the system to low temperatures, the emission is still the zero phonon line contribution is just again 4 to 5%. So that give an opportunity to couple the system to some photonic structures and to suppress all these transitions and get maximum emission at zero phonon line. The alternative option is to probe systems which has a very, very less phonon sideband contributions, for example, like in 2D materials, but it has also got some other disadvantages. And ideally, one should expect for a NV sender an intensity versus lambda spectra should be like this. Okay, this is not a measured one. This is what I drawn with my hand. So you can see that all emissions are suppressed. Only you get an emissions at 640 nanometer, which is basically your zero phonon line transition, and which is a coherent transition, not decoherence system. So it will be some nice stuff to do many quantum applications using that wavelength. So so those who are not in the field, this how the sample look like. So usually we classify samples into two broad categories. What we call is a bulk diamond samples. Basically, it is grown either using CVD or high pressure, high temperature growth. It looks like a piece of glass piece in your hand, something like this. And you look for some emitter doing an imaging, a confocal imaging, which I'll tell you later in detail. And you spot, okay, there is some emitter, and you measure the properties. This is a real sample picture from our lab. We have 4 diamond samples from an industry, and you can see that the different colors it has because of the different kind of defect centers in that. The other class of samples, we people also use nano diamonds. Basically, these are 5 to 100 nanometer diameter particles, and these particles will have a NV sender in it. And this comes like a colloidal suspensions to you. You can buy this commercially, and it looks like slightly milky in color, and you can dilute it and use it. So one of the basic problem with the diamond in terms of collection of photons, diamond is a very high refractive index material. It has around 2.5 refractive index. So the total internal reflection angle is so small, so most of the light is getting trapped within the system. So the collection is very minimal. So one solution is to go for nano diamonds. So the sizes of even much smaller than the wavelength of emissions. So you can get more light extractions. Or you create photonic structure in these diamond systems, diamond samples, and to avoid or to enhance these emissions by manipulating the density of photon states. So there are 2-3 trade-offs in this business, and we'll tell you some of this, how we do that. And many applications have been forecasted. Some are even commercialized. Like another important thing with NV sender, like unlike quantum dots, does not photo bleach or no photo blinking. So it's a good system for biomarker in many applications. Nowadays, we are also started some research recent where we integrate this NV sender with the cells and other things. So you can locally measure the local magnetic field and other kind of sensing protocols. And this has been used as a NV center, as a magnetic field mapping, like what we call magnetometry. This is a technology which is now commercialized by Kunami. And one can buy this NV magnetometer commercially, where, as I said in the previous, these energy level diagrams are very sensitive to magnetic fields, and you can manipulate the magnetic properties. And the other sensors like a temperature or other things, so you can do a microwave-based experiments, and those kind of experiments also people are done. And mostly for the other aspects which got very excitement in this NV center, when it gives us a nice single photon emissions at a room temperature, where people measured intensity correlations or the G2 function and show that a dip at 0 time delay is a signature of single photon source. I'll tell you at the last my talk some of our experiment towards these aspects, what we did at IIT Ropar. Okay, so even I said a lot of nice things about NV senders, and there are so many challenges to also overcome. As I said, one of the biggest challenge here is that you have a very broad phonon sideband emissions and a very feeble zero phonon line. And zero phonon is something which everybody's looked for in the systems with the maximum emission at 637 nanometer. So one need to suppress these emissions. And the other issue is that when you pump the system for a long time, there can be recombination and ionization. So NV minus may convert to NV zero, and which is something you don't want to do happens. And the lifetime, if you measure the decay rate of these NV centers, the lifetimes for nano diamond is even some 30 to 40 nanoseconds. And for bulk diamond system, it's around 10 to 12 nanoseconds. So it's a very, very slow emission process. One is to increase this emission rate so that one can have a more bright on-demand single photon sources. So the one way out to all these things is to couple this system with photonic structures. And that's what we do, and we are going to discuss today. So why photonic structure is very interesting for this purpose. If you know the basic quantum mechanics, that the decay rate is proportional to the dipole moment and the density of photon states, what we call the Fermi's golden rules. And if you look at these equations, if you want to manipulate the spontaneous emission rate, the gamma, you need to manipulate the density of photon states. And it was proposed long back in 1987, this engineered photonic structure like photonic crystals or even a photonic cavities, while you trap an emitter, you can control the rate of spontaneous emissions by manipulating the density of photon states around these emitters. So we did a lot of work, not with NV senders, with other quantum emitters long back. So our first attempt was, why not combine these kind of dino diamonds with the photonic structure and see the possibility that yes, we can at least somehow control or exercise some reliable control on these emission properties before you go into more sophisticated experiments. And I'll tell you that in a moment. So so what are the different photonic structure people in the literature, what people have been using this for purpose? One of the system is a pillar cavities. Basically, you have a dielectric layers and there is a cavity here. You trap this NV sender in the cavity layer and manipulate the spontaneous emissions. And the other system what also proposed is that nano beam cavities where you have a periodic array of holes and you trap an NV center at somewhere in the system and you can enhance the density of states and enhance the emission at the 640 nanometers. So these systems are preferentially or deterministically designed to function at 640 nanometer while suppressing all other transitions. Even plasmonic systems are proposed, like some silver cubes strapped with the nano diamonds, and see how much emission rate can be changed. Hyperbolic metamaterials have been proposed. Even some Mean resonance systems are also proposed to manipulate. So the people are looking at different schemes and different platforms to manipulate these NV center emission properties with the goal to achieve get maximum emission at 640 nanometer and with a very fast rate at room temperature. So the other systems is also proposed in the last few years where we have a gold film and they trap NV center here, like what they call the single dipole here. Then you have a silver nanocube, a 3 nanometer coating, and then you measure the emission. You can see that while measuring from the reference of the glass, the decay rate is very, very, very slow. But when you measure on a sample, you can see that the decay rate become very faster. So by trapping these emitters in this small region in like in a plasmonic cavity, one can exercise control over the emission properties. And these are not that deterministic because these are all statistical experiments where you don't know where you can actually make an experiment every day like that. But then there are more deterministic structures like you preferentially make a metal layer, then you trap dimolecule or emitters, then you have another metal layer and you grow these samples. And you can see that when you measure the emission as a function of wavelength, the reference sample is showing a very, very little emissions. But when the emission is in the cavity, the emission is enhanced even 50,000 counts in this, like say 260-fold enhancement. Now, if you look at this spectra very clearly, you can see that the emission intensity is enhanced quite huge. It's an unimaginable numbers. But you look at the decay rate, there is no much change in the decay rate where you have a reference sample as well as in the cavity. So this is an important thing when you talk about the emission measurements in cavities or these kind of structures. It's not the intensity is not a sufficient criteria to classify, yes, my structure is inducing a changes to the emission decay rate. One has to do a decay rate measurements because the local density of state is proportional to the decay rate. Okay, you can measure the increase the intensity just by putting a mirror also. Okay, but that does not increase the rate of emission process. So these are the trade-off in the literature what you see here. So so once you make the samples, let's say you may have some photonic structure coupled with NV sender, how are you going to measure it? And that is the most challenging part, especially when you have a single NV senders. So what we developed at IIT Ropar is a confocal imaging setups where you have a 532 nanometer laser. We take this light and towards a high-end objective. Your and the NV sender is, let's say, the structure is on a moving stage. And this is scanned and we collect the emitted light and send it to a APD, an avalanche photodiode, and it's all controlled by LabVIEW. And so we first we generate a map. Let's say the confocal map, you get it within some 100 by 100 micron scan. And there's some maybe an emitter we get here. There is an isolated emitter here. There can be an emitter here. But what is more important here, sometimes this spot may not be an NV sender. It may be a scattering point, some inherent fluorescence from this host material. Okay, so one has to be very careful measuring these emission spectra when you do especially cavity coupled experiments. Once you got a nice plot, okay, we are convinced this is an NV sender. We measure the PL spectra by coupling the light of fiber into a spectrometer. And we also have in our lab a setup, we have one more APD. Then we can do a intensity correlation experiments, what we call it in the Hanbury-Brown TIS experiment configuration. So we can look for single photon emission in the system. We can also apply a microwave or a magnetic field here. And you can see that how we can manipulate this emission using these external feeds. So those who are into this business will appreciate with me that it's extremely tough to get the single NV sometimes. It's so isolated and you don't know sometimes where it exactly. It is as tough as mining diamond in Siberian mines. Okay, so there also people use lights to see. They're looking for diamond samples in the mines, and we are also putting some light and see the fluorescence images to see whether there is a NV centers in our samples. So this is the actual setup picture in our lab where we developed. It took a couple of years for us to reach this level of perfections, where we can do any type of quantum emitters. It's not restricted to NV centers. We can go to 2D material, perovskites, quantum dots, and where we have capability to image the sample. So we can locate the sample, we can measure the PL spectra, we can measure the lifetime or decay rate, and we can do the Hanbury-Brown-Tisse experiment for single photon emissions. So, so this is the experiment setup, and then we make our first samples, basically the photonic crystals samples, where we have a colloidal crystals we have in the lab. This is pretty old work we started in 2017. So this is the way the sample look like when you grow the crystals. These are 3D periodic arrangement of microspheres. It's called as a 3D photonic crystals. And it has a band gap, photonic band gap by at around 660 nanometer, which is this reflectivity spectra. And we made this structure intentionally so that it overlaps with the NV center emission spectra, which is in the blue curve. So when we combine this NV center with the photonic band gap, as per the Fermi's golden rule, we should expect some changes in the emission intensity or rate, and if so, then we can control the emission properties. So this is the experiment we did. For the first experiment we did on NV centers, where we coupled the NV centers to photonic crystals. We excite with 532 nanometer light, we collect the fluorescence emissions. And you can see that when you normalize with the reference sample, the intensity is suppressed in the phonon sideband at 660 for this photonic crystal sample and for 700 for another samples. And one can also see that if you intelligently match the band edge of the photonic band edge with the NV center, we can slightly increase this pseudo-phonon line. Even though there is a huge change in intensity, we are so excited, but if you do the measurement in lifetime, hardly there is no much change. Okay, so this may not be that good system to manipulate, but at least it shows a possibility that yes, indeed, these soft photonic crystals can induce changes in emission spectra. So those who are interested, you can look at these papers published in 18 and 20 in Optical Letters and Physical Review. And later then we thought, instead of having this photonic crystal, which is a multi-layers of structures, can we generate a single layer of polystyrene spheres? So basically we have a low index metasurfaces. And we made these samples. So it was quite painful to get this single mono layer of these polystyrene spheres. And we coupled with NV center, and we measured the reflectivity spectra of the samples. Instead of a peak, we get a 2 dips. And this has been agreement with the field, the FPTD calculations. And one of these dip actually comes because of the grating mode, because these are the grating structures on top. But what is more interesting is that the dip comes at 700 nanometer. And by looking at the field calculation, you can see that there is some field localization in the system. So it actually worked like a small cavity system. And to prove that, we measure the lifetime or the decay rate of the coupled NV center. And you can see that here, the red one is from the reference sample. And when we couple with our monolayer sample or the load index dielectric metasurface, the decay rate becomes faster or the lifetime becomes slower. And so this is also another photonic structure which shows an interesting thing, where we can, at least in principle in the laboratory scale, we can manipulate these emission properties. But these are not that systematic in the sense, these are not deterministic structures. One cannot generate always because there'll be a lot of defects. The refractive index values are very small. So the changes in emission you see is very, very, very minimal. Okay. Even though there's a rich in physics you can do, but in terms of an application perspective, may not be a good system to probe. So we look for alternative system with something which is feasible for us at IIT Ropar, because we do not have much big clean room. So we have to rely on what is possible here. So we look for a structure of what we call as a metal-dielectric structure. It is known in literature as a Tamm structure. So basically you have a multi-layer structure, a periodic variation of dielectric, and on top you have a thin silver layer. Now, if you probe this light, suppose imagine a situation, there is no metal layer now. You incident light and measure reflectivity as a function of lambda, you get this black curve. And you see that there is a range of wavelength where there is no reflectivity is 100%. That means the light is not able to get into the structure. This is basically what we call as a one-dimensional photonic crystal or a distributed Bragg reflectors. Now, what is more interesting here is that when you have a thin metal layer on top, when I say thin metal layer is 20 to 30 nanometer, and you measure or you calculate the reflectivity, what you get is a red curve here. And you can see that at exactly around 640 nanometer, which we designed the structure for 640 nanometer, you can see that the reflectivity shows a dip. And this is something like a cavity structure. Now, how do you prove that this is a cavity? We did a field calculation to that. So when we look at the field calculation in the system as a function of depth, so the field intensity as a function of depth, you can see that the field at 640 nanometer is hugely enhanced near to the surface, because this the metal layer on top and this dielectric DBR will act like a two high reflective mirrors, and it create a localized states at the interface between the metal and dielectric. And this is called a Tamm structure or optical surface states or optical Tamm states. And what is interesting here compared to conventional surface plasmon resonance, it can be excited using both polarization, transverse electric or transverse magnetic, and one can even do it at normal incidence. And this is quite, but the main issue was here is the quality factor, which is the delta lambda, the lambda by delta lambda, which is very small. So the quality factor is small. So it may not be that effective in manipulating the emission properties. So I'll show you how something we did to overcome that. So one can also tune this Tamm mode by changing the spacer thickness. You can get any wavelength you want. It can also vary the position by slightly using metal thickness variations. But if you go beyond certain value of metal thickness, then sample become inactive because metal become highly reflecting. Then you can't do any optics with that. It simply become a metal film for you. And these are simulation results just to show you that it can excite at both polarization, even at normal incidence, and it can an angle tunability. So this system is quite interesting. And then we thought about how to increase the Q factor, how to increase this system. So we come with a very simple idea that, okay, you have a conventional Tamm structure here. And on top of that, we create one more small DBR, may not be the equal number of layers. And in a way, you create two dielectric interfaces. You have a DBR structure here, you have a spacer one, and you have metal here. Then you have another spacer here and another DBR here. So DBR1 and DBR2. So it's like the double structure you have. And we did some simulation to see whether it can give me some better performance than the conventional Tamm structure or conventional metal-dielectric structure. So as expected, when we calculate the reflectivity as a function of wavelength, we get a two dips corresponding to two interfaces, because I should excite the surface state at between these two interfaces and between these two interfaces. So that's what exactly we see in our calculations. We call it TPR1 and TPR2. And what is more interesting here, the TPR1, which is what we are focusing on at 640 nanometer, which has a higher Q factor than the conventional Tamm structure. And how do you confirm that? When we did the field calculation, you can see that the field is at 640 nanometer is quite enhanced. Even it is got 50 times enhancement compared to the field you hear is just around 18 times in the conventional Tamm structure. So when you have a field is so high, the density of states, the dipole dot electric field. So if you are aligned, the electric field intensity is so large, you can expect to have more control or the more enhancement in the emission decay rate. And this enhanced field localization will induce a increase in density of states for a given dipole moments, and that will increase my gamma. Okay, that's what the whole idea on this work. So we looked at the emission directionality or the far field radiation plot. You can see that at 640 nanometer, this pink line, it's got enhanced, but all other wavelength, it doesn't work properly because that is not the resonance systems. And we simulated what the Purcell factor, which is a black curve here. You can see that close to 640 nanometer, we get a higher Purcell factor. And not only Purcell factor, the light collection efficiency, the amount of light which you can collect by your objective is also enhanced by this kind of structures. And this was recently published in Advanced Quantum Technology. And now we are making samples to prove these experiments. And I'll show you some very recent result of our experiments in this direction. So we fabricated the sample in collaboration with IIT Kharagpur. We have a DBR here, and they were PMMA, which is, and then we have NV centers, isolated NV centers, and we have a polymer PVA layer. So this forms the spacer layer. And you have thin metal films of 30 nanometers. So, and we measure the reflectivity measurements. So you can see that there is a dip coming at 640 nanometer. Now, practically, now you can see that this Tamm mode or the surface states, which is not stable at 640 nanometer. So depending upon where you measure on the sample, this dip was slight fluctuation in the wavelength. And that is because in the realistic system, you have inhomogeneity in the sample growth, and somewhere metal film may not be so good. So one has to improve the fabrication capability so that you get a better control on this, or the stability of this cavity mode in the system. And we coupled this with the NV centers and with the lifetime measurement. So we have a reference decay rate, which is a red curve here, fitted with some double exponential function, and we got a lifetime of 16.6 nanoseconds. And when we measure on our Tamm structure, where NV centers are coupled to these surface states at 640 nanometer, you can see that the decay rates now become extremely faster. And by fitting, we extract the lifetime to be 7.1 nanoseconds. So one can change that using these kind of cavity structure coupled with NV centers, and we can change this lifetime into almost half the lifetime. So the rate become faster. By engineering more these structures, we can even go to a better number than that, and experiments are going on. So that was, if you look at this structure, for example, you have a lot of layers you have to grow. First you have to have DBR, then you have spacer layer, metal layer. So it becomes practically cumbersome, and every growth of material induces its own defects and irregularities, and that will all hamper your emission properties. So what is a way out? Can we think of a better system than that? And that comes our attention to some of the papers published by basically by Thomas Ebersen group from France. So they have used this kind of a cavity structure, which they call a Fabry-Perot cavity. In fact, it's not a Fabry-Perot cavity, it's something mixture of metal-dielectric system. So you have substrates, and you have a silver mirror, which is 80 nanometer. Then you have a dielectric with some emitters trapped, and you have a 30 nanometer silver layer. They use this structure to achieve strong coupling, exciton-photon coupling, or cavity catalysis. And you can see that they publish this in Nature Communication, PRL, and all those journals. So we thought, why not use this system for NV centers, which has never done before? And if so, what are the challenges we are going to face? If you look at this system, it looks very simple. You make a metal, and you just got a dielectric with some NV center. You have another thin silver. If you show this to an RF sputtering people, it will say it's a 2-3 hours job for us. But for us, at least, to reach a kind of result which I'm going to show you, it takes a couple of years to reach this kind of perfections, because we have huge challenges when we measure NV center. And one of the biggest challenge which you will face if you're going to do this kind of research is that all these dielectric material has inherent fluorescence. And you will be surprised that someday you measure the cavity mode at 640 nanometer, but it is not from the NV centers. Okay, it may be some in background fluorescence from the dielectric material getting enhanced due to the cavity. So one has to be very careful doing these experiments and painstakingly capture the nano diamonds and coupled with the cavity. And it can also happen, this problem, this diamond, nano diamond or NV center may be coupled with the cavity properly and may not be this one. So you have to do a lot of spatial dependent measurements, and I'll show you how we did it to isolate this exactly which nano diamond or NV center coupled to the cavity. Okay, so we made the sample. First, we simulate the spectra, which is these green symbols you see here, and it shows a cavity mode at 640 nanometer as a dip in reflectivity. And when we measure the reflectivity in our lab, you can see that we exactly get what we want, and the cavity mode at 640 nanometer. But what is here, one can argue with me that the Q factor is small because this cavity with this broad cavity mode you have. But due to this metal dielectric confinement, the system is actually give a very good Purcell effect. And to confirm, yes, there is a field localization here. We did some simulation in the structure. We see that there is a field localization within the cavity structure. And you can see that at 640 nanometer, there is an enhancement of emission density. So then we did the experiments. We made this sample with a lot of NV centers trapped in this dielectric layer. And we look at our confocal mapping, 100 by 100 micrometer. And you can see there are a lot of bright spots. Some may be NV, some may not be, maybe dust particles. So we look at some positions, we convince, okay, this guy belongs to a NV center. We measure first a reference with the cavity background. That means the emission from the cavity layer without any NV center. And you can see that here, the green curve here, which shows the peak in emission at 640 nanometer. And if I show you the spectra, you will not be doubting me, right? Because it shows a nice cavity mode at 640 nanometer, exactly we want. But this is the wrong data. This is not NV center, this green curve. This is the cavity background. And then we did on an off cavity structure, you get a red curve, which is the expected fluorescence of the NV centers. And now we have a cavity sample. You catch an NV center which is coupled with the cavity. What you get is a blue curve at 640 nanometer. And to be more clear, you can look at this insert picture. where the red one is NV center not coupled to the cavity, which shows its inherent fluorescence. But when NV center coupled to the cavity, you can see that these phonon sidebands are suppressed in both sides, and the emission got enhanced at the 640 nanometer, which is a zero phonon. And that was our goal, to enhance the emission at 640 nanometer. As I said in my previous slides, thus the intensity enhancement is sufficient to confirm that the rates are increased, or there is an increase in density of states. So we did a lifetime measurements. So we pick one of the image from the samples, one of the spot of NV centers. We measured the decay rate of the NV center as a function of time. So you can see that this one is a bare sample, or from a of the cavity sample, the resonance is around 25 nanoseconds. So the lifetime. And when you do the cavity coupled NV center, the lifetime is 6 nanoseconds. So you can see that the inherent lifetime of 25 nanosecond in a dielectric medium is brought down to 6 nanosecond by coupling this NV center with the simple cavity structures. And it's a huge change. If you look at the fabrications aspects, is a very good achievement. Now the question is, do all our NV centers show this 6 nanosecond? The answer is no. So if you look at, so what we do a statistical measurements. We catch NV centers at distributed over the samples, and we measured different NV center. And there are samples which there are, so for example, around 8 NV centers will give you a lifetime of 10 nanoseconds, and even there are NV centers which give a 50 nanosecond. And why so? Because these NV center may not be exactly coupled with the cavity field, so they may not be getting exact field enhancement what we are expected to be this system to behave. And you can, but still at any rate, you can see that if you compare with my reference sample, the fluctuations is much different each other. They're not overlapping, and average we can get a lifetime is around 10 nanoseconds compared to some 25 nanosecond in the reference sample. So this is a way we could show that by coupling NV center to these cavity structures, one can completely suppress this phonon sideband and get emission enhancement at 640 nanometer. So let's come to the last part of my talk, where we'll show you some of our recent experiments to generate single photon from these samples. Because if you remember all these samples which I'm talking about, there are more than one NV center, because there's no single photon emission we could not detect. So single photon, basically I excite and I get a one photon per excitation. So I excite, then I get a single photon, then I excite, I get a single photon. And I need to generate it deterministically with a bright single photon source, and which has applications in many quantum technology like quantum key distributions, random number generation, quantum metrology. So theoretically, we classify the single photon nature using a G2 function, which is an intensity correlations. Basically, you look for a coincidence of the photon intensities in two detectors at 0 time delay. And if you get a, theoretically, you say that, okay, if I get a G2 0, that means there's a single photon emission. That means only one detector got a photon and the detector did not get, so correlation becomes 0. So we made some samples. We deterministically made some diamond samples where you have NV centers distributed everywhere in the systems. So this NV center could be a single photon source, may not be. So we have to do that. And so we took a confocal image of 20 by 20 micron, and let's say we pick one point, and we look at the PL spectra. That's the first thing we do in experiments to see, yes, there is a phonon sideband, there is a zero phonon line, and so on and so forth. If we convinced that yes, this indeed have a NV center, and you can also see, because of the quality of the sample is so good, the Raman line is also visible of the diamond. Then we measured the lifetime in our confocal, and we got around expected around 18 nanoseconds. And then we did intensity correlations. Basically, I have a diamond here. If it is a single photon at 0 time delay, either it can go to detector D1 or it can go to detector D2. So I look for this coincidence between that at 0 time delay. And if the coincidence is 0, that means there is a single photon. And that's what we measure in experiment here. These points are from the experiment. And you can see that the measured G2 value is much close to 0. And if the G2 at tau equal to 0, 1 minus 1 by n, and n is a number of photon. And if n equal to 0, that means you have, for n equal to 1, that there is a single photon, the G2 equal to 0. So this is what that we measure in the lab, and we can even have single photon sources from our diamond samples. And the G2 value which we got is 0.1, is almost close to 0, and it is such a nice single photon source. But you should remember that this measurement is done at room temperature. And the last part is, as I said in the beginning, that one can manipulate these states using microwave and optical fields and do this optically detecting magnetic resonance. So what we have is we excite the samples using 532 nanometer. You lift the population to the higher states, and it can come down to the industry system crossings. Then you apply this microwave 2.8 gigahertz. You can lift the population from the ms equal to 0 in the ground state to the in the ground state to the ms equal to plus or minus 1 state in the ground states. And then this state then become the dark states. Basically, the emission intensity become low. And if you look at the emission intensity as a function of microwave frequency, so when you apply microwave of around 2.8 gigahertz, there is a drop in emission intensity because there is not much population in the ground state to go to the excited states. So this is a simulated curve, and I'll show you how we did experiments. So this is what basically happens. You have a nitrogen vacancy center. You, let's say in the step 1, you start with an equal population in the ground states. You excite with the 532 nanometer laser. The population goes to the excited state in the step 2. Now this population can come down either straight line, straight from the excited to the ground state, or they can take this intersystem crossing through these metastable states. So, and this is a spin conserving transition. So in the step 3, you have a more populations in these ms equal to 0. You start with, let's say, 2 electrons or something, and now you have more than that. And now you apply a microwave source, which is 2.8 gigahertz. This population is lifted to the plus ms equal to plus or minus 1 state in the ground states. So you have a more population lifted in the step process. So that means the emission intensity goes down in your PL spectra because that is not the that is now become a dark state. So this is what we did in the lab. So at magnetic field 0, we measured the PL count as a function of microwave frequency. At around 2.87 gigahertz, we see that there is a drop in emission intensity. And this is what we expected. And these measurements and the fitted with the measurements are fitted with the curve nicely. And what happens if you apply magnetic field now? B is not equal to 0 because these levels, these ms equal to plus minus 1 levels in the ground state, these are degenerated 0 magnetic field. And so when we apply magnetic field, it can split using like Siemens splitting, and you have now transition, population transition from between these two levels in ms equal to 0 to plus minus 1 level. So we expect you have 2 dips now, and that's what. And this is the basis of the sensing magnetic field. Now, by calculating the difference between these two splits, these 2 dips, one can recalculate what is the magnetic field at the NV center positions. Okay, so this is something which we just recently, a few weeks back, we did this in the lab. We are successful in the lab. So with that, I conclude. Hope I able to tell you some of the exciting properties of these NV centers and its advantage, what is its use, and how important these photonic structures to manipulate its light emission properties. Okay, so some of the things we are right now we are looking is that these, because whatever result I presented all in room temperature. So when we are looking for low temperature and emission experiments, and to do, now we got single photons and spin manipulation experiments. Now we are going much ahead with that, how to couple these systems for and get efficient single spin photon interface and so forth. So, so I give talks, so I thank my students, my PhD students, and one of this work, this cavity work is a part of Drisha master project. She's from IISER master student. She was funded by the Chanakya Fellowship from your IISER Pune Institute. And I also thank my previous students who begin this work, set up the lab experiments, all the funding agencies, and my collaborators. And if some of you are interested for PhD or postdoc, we have positions available in quantum technologies. And this is my group. And with that, I thank you and for this time. And if you have any questions, I will be happy to discuss with you.
So now the floor is open to the question. If anyone have any question, please ask. Then I will ask my questions. Okay. So, sir, I am asking some question like you were talking about nitrogen vacancy in diamonds. So how one can create this kind of nitrogen vacancy experimentally?
Yeah. So people, what we do, what we understood is that we don't do any fabrication. We get this sample through collaboration of friends. So they have this diamond crystal with the carbon atoms. You bombard with the high energy beams. They throw these carbon atoms away. Okay, and they then do ion implant with nitrogen atoms preferentially. Okay, so you place deterministically these nitrogen atoms in the systems. Then you anneal the sample at very high temperatures, and this system get diffuse and stable, and that way you create nitrogen vacancies. So if you want to create a silicon vacancies, you implant the silicon atoms. This is one way to do deterministically artificially. But what happens sometimes during the growth of the samples in the CVD chamber or whatever technology they use, this can also come as a impurity in the system. But that may not be a deterministic system. So you always have nitrogen vacancy there.
So in one of the experiment, what you have shown, there you have shown that your stage is moving and you are recording the data.
Yeah.
So why that is so?
Because we doing because as you look at the confocal images, these images are, let's say, by 20 by 20 micron area.
Yeah.
So we have to scan the sample like a laser scanning with your 532 nanometer, and you are capturing the emission intensity. Okay. Then in the back of the computer, our LabVIEW program create an intensity map for you.
Okay.
So then you know, okay, there is an emitter here, and then you go back to that position, measure the emission intensity.
Okay. Basically, you are taking the spectra pixel by pixel, so
yeah,
that you can map the whole sample 100 micron by 100 micron. Sample.
Yeah, correct. Otherwise, we will not able to get this NVs, and especially when you work with these samples which I shown you, which has only one to 4 NV centers. It's conventional technique doesn't work. You need to do a lot of experimentation and instrumentation to collect these emission signals from the samples.
Okay. And there is one more basic thing that I don't know. Actually, it is like you have talked that people use nano diamonds also, and there is also NV center. So how these two things, like bulk system and nano diamond, and bulk system and NV center, and the NV center in nano diamond differs basically.
Okay, one of the so your question is over?
Yes.
Okay, so the primary thing initially, because you can't making photonic structure in diamond will be a very tough thing, etching, and yes, people tried it, but in literature there are few reports. It was not successful in terms of its performance. But the advantage of nano diamond is that this can make it in 10 to less than 10 nanometer. So one can easily couple with these cavities or integrate with the cells and for sensing and other properties. So it basically will look like a quantum dot for you, but it does not do photo bleaching or anything because emitter is NV center. So that is the why the industry was moved towards nano diamonds, and you get more commercial product nano diamond than the bulk sample because people use more nano diamonds for all this work.
Okay, sir. So, like how you measure the single photon thing, like single photon emission?
Okay, so what we have is for example, if a light source, okay, so suppose if I emit only one photon at a time, okay, that's like you have a bullet, one bullet is coming. So now you have a 50-50 beam splitter here. So at 0 time delay, this photon either can go to detector D1 or detector D2. Okay, if it is single photon, both D1 and D2 cannot get photon at the same time, right?
Yes.
So it can either get D1 or D2. So what we look at these intensity correlation between I1 and I2. So this counter will calculate that correlation, and if the D1 get a single photon and D2 do not get, then correlation becomes 0.
Yes.
So that will come as a dip in your autocorrelation measurements. So that way we can measure it, and in literature what you see is that if the dip goes below 0.5, that means it is one photon is emitted in your system.
Okay, sir. Sir, and in this slide also, like in the top one where you have shown the time scale, like decay time scale and all. So how people probe that small time scale, like it is in the nanometer order?
This one.
Yes, nanosecond order.
Yeah, this is again the time correlated single photon counting techniques. So our system can measure, let's say, a lifetime with an accuracy up to 100 0.1 nanoseconds. Okay, sorry, 80 picoseconds. Sorry, 80, 100 picosecond is our resolutions. So using a APD and this stopwatch or this, you probably know this TCSPC module,
Yes.
time correlated single photon counting. So
Yeah.
that counting technique, one can measure this nanosecond. This is a pretty standard thing. Even commercial system is also available. Okay, but when you go to very high, low lifetime level like picosecond and all, then you need a streak camera and other stuffs.
Okay. So a few more questions. Sir.
Yeah, please.
You told that this NV center is the spectra of the NV center basically shift or changes with magnetic field.
Yeah.
So how much magnetic field is needed? Is there some sort of like, is it a global magnetic field or local magnetic field can also be proved like this way?
Yeah. This is a local magnetic field only. So in our measurement, these are few millitesla. Okay. But in literature, because people are reported and that even people can go to accuracy of even femtosecond measurement. Okay. So locally you can measure, suppose you have some biological species cells where you have a local magnetic field you have to measure, which is in some nanotesla, femtosecond. So people are integrating this nano diamond with these cells and do an ODMR measurement similar to what I shown. Okay. So this is a local magnetic field at the system.
Yes. So then just one more question, last question.
Yeah.
Sir, you have shown a 1D photonic crystal. On top of that, there is a, I think, silver film.
Yeah.
So in this, you have shown that why is this oscillations coming and how AG is basically playing a role, or silver film is playing a role here.
Okay. So basically, you have a 1D photonic crystal. Yeah. Okay. And then you have a top blue layer. You in this picture is a dielectric layer.
Yes.
Okay. And on top you have a silver layer. Okay. Yes. So if you look at this, if you forget about the silver layer for a moment, this when you incident light, this photonic crystal, 1D photonic crystal will also work like a high reflective mirrors in this wavelength range. Yeah. Correct. And when you put a thin metal film, let's say 30-40 nanometer, this metal film is also a high reflecting film. Okay. Right. So you create a kind of a cavity between using this DBR and this metal film, and this blue top layer become a cavity layer. Okay. So you localize this light between the metal layer and this DBR. So in a conventional fabric or a cavity, you have two mirror and a dielectric medium between that, right?
Yes.
So, and you get a feed localization within the structure. Yeah. But here, our cavity layer is in the top. So that is why we call this is a surface states. Yes. Okay. So this is not, and how do you know that it is a surface state? You do a field calculation. Yeah. So you can see that the field is enhanced at the surface between the dielectric DBR and the metal layer. Okay. Yes. So that's what. And these oscillations are the field calculations. Okay.
Yeah. Basically, it is showing the localization of the field, no?
Yeah. This is, for example, if you this right picture, the red one is localization and enhanced at the surface, and it is slightly penetrate in the medium at 640 nanometer. But if you send a 540 nanometer light, which is somewhere here, which is in the DBR, it cannot go. It reflected back.
Yes. Yes, sir. My questions are over. Yeah. And yes, sir. It is really we enjoyed a lot, sir. Thank you, sir, for such a nice presentation.
Okay. Thank you for your time and to listen to me, and thanks for the invitation again.
Yeah. Thank you.
Bye. See you. Bye.